Hello friends, so today we will proceed with another recording. The topic is analysis of side data and we are referring to case 2 when bridge is just outside the curve. There are like 11 cases which we will go through in this course, and ours is case 2, and we are referring to the first case, that is bridge 441 up in Barabanki, Lucknow up 9. This is the case that we are going to look into. We have already prepared the slides for this video. This is about the recorded video which will come here. So the data is something like this. This is our bridge, 5 span bridge, 1, 2, 3 span. You can see 4, 5 are here along this direction towards Lucknow. This is abutment A1. This is A1. This is view towards Lucknow, that is towards increasing kilometer. This is A2. And in previous slide we have this is A1, and towards BBK, that is towards downline, there is a TTP2. There is a TTP2. As you can see, there is a curvature here, and TTP2 of curve is approx 170 PRCs behind A1. 170 PRCs approximately. And so what we do, that we will draw a line joining A1 and A2. We will extend it backwards and we will see what is the TTP2 alignment with respect to that line. Ideally, TTP2 and all points between TTP2 and A1 must lie on the same exact line as A1-A2. That is to say, the approach transition length, the approach terminal tangent rather, should be on the same line as the bridge alignment. So this is our bridge alignment. This is our bridge alignment, and TTP2 is behind this 170 sleepers, and it should lie on the same line joining A1 and A2. So this is the fastest solution that we have approached here. We have not taken all the data of the curve. The curve has 18 stations, station number 0 to station number 18, that is TTP2. In the side data that we have, we are going to plot in AutoCAD, we have not lifted any data behind TTP2. That is, we have not taken the location of curve station points. We have only plotted till TTP2. This is A1 RR. A1 has been repeated 2 times, so we have 3 readings for A1, this one, and this one. We will select the middle one as the right location, and for A2 also we have 3 readings, this one, and there is one more somewhere here only, this one. So we will select the middle one, that is this one, as the right data for A2. And this is concerning the left rail, that is to say this left rail inner edge of the railhead. That is the data we have selected. And in AutoCAD file you can see other data like S5R2, S5L2. These refer to span. S5 means 5th span. Likewise, S4 means 4th span. S3 means 3rd span. S2 means 2nd span. R1 means first point towards right. L1 means first point towards left. That was covered in the presentation of nomenclature, and that represents a point on the top of stringer. Station marking on girder edge for alignment analysis. If we want to analyze girder to girder alignment, then we mark these points which are 2 inches inside the edge of the, like this is the edge of the top stringer, and then we place our prism pole right at this intersection here, which represents a point inside 2 inches of the edge, and we have given nomenclature to them as S2L1 or S2R1. So the first 2 points are L1 and R1. The second 2 points on the span 2 are S2R2 and S2L2. L refers to left, 2 refers to second on the left, R refers to right, R2 refers to second on the right. So just another explanation. This is span 1, and span 1 R1 and L1 are here, and span 1 R2 and L2 are here. Then here will be span 2 L1 and R1, and here will be span 2 L2 and R2. So this is the nomenclature. So for the analysis, for this analysis, we will not be using the span points. We will be only using, like, P1 refers to, again, P1, then we have P2. P1 and P2 refers to a point on rail head in the middle of the spans, in the gap between the spans, that is to say, somewhere on the top of the rail head between the two spans. Okay, so that reflects our alignment actually. So that has been taken for alignment analysis within the span. Our purpose right now is to correct the approach PRC track alignment. So for that we will join A1 and A2 of the track, A1 and A2 of the data. So this is A1, we will take the center of the 3 readings, and this is A2, we will take the central of these 3 readings. Alright, and then we will extrapolate it backwards. We will extend it backwards. Maybe they are not on the same plane. Let us check. Control 1. We will make z values 0. Then we will again try. Just a minute. Alright, so the issue was this view problem. So we made it view from top, and then we draw the line, and then we extend this, select the line, extend, and this is the standard. So the line joining A1 and A2 has been extended backwards. And just one more thing to give you some more context. This is A1. This point represents M3, that is M30. M4, that is M40. M4, that is M40 means minus 40 PRC. So this gap is represented by 6.4 meters, approximately 10 PRCs. M5 means M50, minus 50th PRC. Likewise, we have gone till M12, M12, M11 in fact, that is minus 110 PRC. Then we have gone to M12, but this distance is not actually 10 PRCs. This is a station marked on the rail web, which is plus 3, then plus 2, then plus 1, and then TTP2. So TTP2 के आगे जो स्टेशन plus 1, plus 2, plus 3 मार्क रहता है, वो हमारा यहाँ पे है, जो कि 10 मीटर गैप पे approximately है. Okay, and so now we need to see that इसमें M2 और M1 नहीं है. That is because it was not visible due to obstruction from OHE mast. So we don't have data for that. And we have this M3, and this direction is towards up line, this direction is towards down line. So this is the increasing kilometer. So we can see that M3 point is lying towards left of the ideal alignment. And what is the offset here? So we can see that this offset is 12 millimeters, and that is what we have entered here, that is 12 millimeter. M30 needs to be slewed by 12 millimeter towards right. Alright, 12 millimeter towards right. millimeter towards right. This value we have filled it. Then M40, let us see the case for M40, that is minus 40th PRC. This point is also towards left, so it needs to be slewed towards right. And by how much? So that we can see it needs to be slewed towards right by 15 millimeters. 15 millimeters. So that is the value we have chosen 16 as even number. We have chosen 16. Then likewise M5 needs to be slewed towards right by 13 mm. We have chosen 14 as the even value, just 1 mm extra. We have gone on the higher side because the machine usually tends to slew less than required. Then this is 17 mm, so we have gone to 18 mm on M60. So likewise we can find the slew values, required slew values for M6, M7, M8, M9, then M10. M10 it is coming 68 mm. M10, that is M100, it is coming 68 mm. Then M11, it is quite far, it is coming 88 mm. M12, which is plus 3, it is coming 104 mm. M13, that is plus 2, it is coming 133 mm. M14, that is plus 1, it is coming 159 mm. And TTP2, which is the station number 18 of the curve, it is coming 186 mm. So these values we have filled here. Okay, this is represents TTP2, and our main analysis in AutoCAD ends here, because the main thing we are going to do here is basically we will taper out this slew value, that is slew towards right, by small values. We will taper out, that has been shown here, tapering out. But how we will do that, we will see when that will complete our analysis. We have not gone till CTP2. CTP2 would be somewhere here. We have not analyzed the location of CTP2. We have not analyzed how much slew is required at CTP2. We have not used the formula. We have not used this formula y equal to x cube by 6RL, where is y is the y-ordinate with respect to terminal tangent, x is the longitudinal distance from TTP2 in meters, r is radius of curvature of circular portion, and L is the overall length of transition. We have not used this formula also. We have only found what is the required slew at TTP2 and then linearly tapered it out. However, the linearly taper is not exactly linear. If we want to linearly taper out 186 value and there are 18 stations, and we intend that the slew at station number 0 should be 0, so 186 divided by 18, it will become approximately 10.5, so 11. So if you reduce this value by 11, this minus 11, so this is what we get. And let us make this 0, 0, 0. Alright, this is the required slew. However, what happens is that here it is 186, here it is 175. Suddenly we have gone to slew value of 11, and then again 11, 11 by reduction of 11. So what happens is that when we linearly taper out, then terminal stations, mathematically such shaping is done where every successive station is slewed by a value 11 mm less than slew at previous station. Terminal stations will have change in the reservoir signs by 5.5 points, whereas there won't be any change in word signs of intermediary stations. So basically what we are saying is that intermediary station, that is station number 16 to station number 2, there won't be any change in word sign. However, at station number 17 there will be a sudden change in word sign of by 5.5 values, and so also at station number 1. Basic premise is that if we want to taper out, then reduce this value slowly first and then increase it. So what we have done is we have reduced it by 6 only, so we have got it 186, and after that we have, because see, this is the ideal case I have taken, so I am using that example. So here it was 186, here we have used 180 as slew, then that was a reduction of 6 from 186, then by reduction of 10 from 180, that becomes 170, as you can see here, then reduction of 11 from 170, that becomes 159, then reduction of 12, so 147, again reduction of 12, 135, again reduction of 12, 123, again reduction of 12, 111, again reduction of, now reduction of 11 only, so becomes 100, now again reduction of 10, so that becomes 90, reduction of 10 becomes 80, reduction of 10 becomes 70, reduction by 10 becomes 60, reduction by 10 becomes 50, reduction by 10 becomes 40, reduction by 10 becomes 30, reduction by 10 becomes 20, reduction by 10 becomes 10, then reduction by 5 becomes 5, then 0, 0. So in terminal positions we have used a small reduction factor. The reduction is by small values. So this is the selected one, so let me hide it. Alright, so this is the this is one of the shortest way to solve the problem. We have found the required slew at TTP2 and then linearly tapered it out. All the slew was towards right, so this is also towards right. Now we can divide this slew value into 4 parts, because maximum slew is more than 150 mm and less than 200 mm. The machine can slew only 50 mm in one tamping. So first round of tamping, since we don't have the data for 10 and 20, we have used triangulation. So at minus 30 it was 12, so minus 20 we have taken 8, and minus 10 we have taken 4, 16, 16, 14, 14, 18, 18. We have copied it till 48, 48, and instead of 68 we have used 50. This is the stage 1 slewing. This is stage 1 slewing, and this 50 we have taken till here. Then again reduce the value 40, the same values have been copied here. So this gives us a stage 1 slewing. Stage 2 slewing, here it will be equal to 48 minus 48 equal to this, and then we will draw this till here. Again the values which are more than 50 will be entered 50 only, till here. Alright, so this gives us a stage 2 slewing from minus 90 to station number 5. For station number 3 slewing, let me delete these values. For stage 3 slewing, we see it will be also towards right. This will be 0, this will be equal to 68 minus 50 minus 18, which will be 0, and we will go up till here. We see this is 0, 0, so we delete this one. We see this is 0, 0, we delete this one, and wherever it is more than 50 we will make it 50, 50, 50, 50, 50 and 50. And stage 4 slewing will be this equal to 88 minus 50 minus 38 minus 0, enter, and till here. So these values are 0, we will delete it. These values are 0, we will delete it. And these are less than 50. So this is one way to find stage 1 to stage 4 slowing. Another way is what we can simply do, copy and insert. We can simply, let's put it 4, this is 8. We can simply make average, not average but divide by 4 times. This will be equal to this, divide by 4, enter, and simply find the values. And in format cells we reduce the decimal to 0, and this is the value. So 1/4 of slewing, 1/4 of slewing. This is also one way. This is also one way, and this is second way, and this is one way. So you can use either of the two. If you use this case, in all 4 cases you will have to time from M10 to -1 station number. So amount of time taken will be more, and if you use these methods, this method, then time taken for typing will be less. So this completes our analysis for this case. There is lift also required, that will be explained in other slides. So this is our analysis for bridge number 441 up. Text has been written in the slides also for better understanding, and this is the required slew: stage 1, stage 2, stage 3, stage 4, stage 1, stage 2, stage 3, stage 4, or we can simply divide these values by 4 to get slewing in each case.